When terminating conductors from a generator circuit breaker to two manual transfer switches, several options exist. The generator has a 1000 amp breaker, and the feeder cables will terminate into the lugs of two 1200 amp manual transfer switches. There is enough space for two 4-inch conduits to run from each manual transfer switch to the generator circuit breaker. Each manual transfer switch can supply a full load. The generator circuit breaker has lugs for three 500 MCM per phase, and the manual transfer switches have lugs for four 600 MCM per phase. The initial plan was to use four 350 MCM per phase, with two 350 MCM per phase per conduit times 2 to each transfer switch. This would result in 8 350 MCM per phase being terminated to the generator circuit breaker. The idea of using a power distribution block was considered, but finding one with 8 350 MCM inputs proved difficult. Here are a few potential solutions. Option 1 involves using parallel conductors from the generator circuit breaker. Three 500 MCM cables per phase can be used from the generator circuit breaker. These three 500 MCM cables can be parallel to create a 1500 MCM equivalent cable. Then, two parallel 1500 MCM cables can be run to each manual transfer switch, resulting in a total of 8 cables per phase. Finally, all conductors can be terminated in the manual transfer switch lugs in parallel with 4 cables per phase. Option 2 involves using a power distribution block. A custom fabricated power distribution block can be installed with the following configuration. Input 8 350 MCM lugs and output 4 600 MCM lugs. The 8 conductors from the generator circuit breaker can be terminated into the input lugs, and the 4 conductors to each manual transfer switch can be terminated into the output lugs. Option 3 involves increasing the conduit size. The conduit size can be increased from 4 inches to 6 inches. 4 500 MCM cables per phase can be used, with 2 per conduit. All conductors can then be terminated in the manual transfer switch lugs in parallel with 4 cables per phase. Option 2, using a power distribution block, is often the most practical solution. It provides a clean and organized distribution of power while reducing the number of connections at the generator circuit breaker and manual transfer switches. A custom fabricated power distribution block specifically designed for this application would provide the optimal solution. Additional considerations include firstly ensuring the power distribution block has sufficient ampacity and fault current rating for the generator circuit breaker. Secondly, comply with all applicable electrical codes and standards. Thirdly, consider using a cable tray system to manage and support the large number of cables. And fourthly, provide adequate clearance and access for maintenance and troubleshooting. In more detail, let's consider conductor ampacity and appropriate sizing. According to the National Electrical Code, the ampacity of conductors must be sufficient for the load they will carry. The ampacity of 350 MCM copper conductors, 600 MCM copper conductors, and 500 MCM copper conductors needs to be checked against the expected load and adjusted for ambient temperature and the number of conductors in a raceway or cable. The National Electrical Code Table 310.15.8.3 provides adjustment factors for more than 3 current carrying conductors in a raceway or cable. When conductors are installed in parallel, they must meet the requirements outlined in the National Electrical Code section 310.10h. This includes ensuring that all parallel conductors are the same length, conductor material, size, have the same insulation type, and are terminated in the same manner. Overcurrent protection is also important. The overcurrent protection for the conductors must be sized appropriately to protect the conductors from overload. The overcurrent protection device, such as a circuit breaker or fuse, should be sized according to the conductor ampacity as specified in the National Electrical Code Table 310.16 and other relevant sections. The available fault current at the generator circuit breaker and manual transfer switches must be determined. All components, including conductors, termination lugs, and the power distribution block, must have a short circuit current rating equal to or greater than the available fault current. This ensures that the equipment can withstand the stresses during a fault condition. Coordination studies may be necessary to ensure that the overcurrent protection devices such as the generator circuit breaker and the manual transfer switch breakers are properly coordinated. This helps to minimize downtime and prevent cascading failures in the event of a fault. Proper termination techniques are essential for ensuring reliable and safe connections. Conductors should be properly stripped, and termination lugs should be correctly sized and installed according to the manufacturer's instructions. The use of appropriate tools, such as torque wrenches, is necessary to ensure that connections are tightened to the specified torque values. Grounding and bonding are critical for electrical safety. The grounding system must comply with the requirements outlined in the National Electrical Code Article 250. This includes ensuring that all metallic components such as conduits, enclosures, and equipment frames are properly grounded and bonded to provide a low impedance path for fault current. The selection of appropriate termination lugs is essential for ensuring reliable connections. The lugs must be sized correctly for the conductors being terminated and must be compatible with the equipment they are being connected to. Lugs should be made of suitable materials, such as copper or aluminum, and should be listed for the intended use. Conduit fill calculations must be performed to ensure that the conduits are not overfilled with conductors. The National Electrical Code Chapter 9 provides guidelines for conduit fill calculations, including the maximum allowable percentage fill for different types of conduits and conductors. Proper cable management practices are important for maintaining a neat and organized installation. Cable should be properly supported and secured using appropriate cable ties, straps, or clamps. Cable trays or ladders can be used to support large numbers of cables and to provide a pathway for cable routing. Clearance and access around electrical equipment are essential for safe operation and maintenance. The National Electrical Code Article 110.26 specifies the required working clearances around electrical equipment, including the minimum width, depth, and height of the working space. These clearances must be maintained to allow for safe access to the equipment for inspection, maintenance, and repairs. All work must be performed in accordance with applicable electrical codes and standards, including the National Electrical Code, as well as any local codes or regulations. A licensed electrical contractor should be consulted to ensure that the installation complies with all requirements. Safety precautions should be taken during all phases of the installation, including wearing appropriate personal protective equipment such as safety glasses, gloves, and arc flash protection. All electrical circuits should be de-energized and locked up before any work is performed. A thorough inspection and testing should be conducted after the installation is complete to verify that all connections are properly made and that the system is functioning correctly. Testing should include installation assistance testing, continuity testing, and voltage and current measurements. The use of a power distribution block offers several advantages, including simplified wiring, reduced space requirements, and improved safety. The power distribution block provides a central point for connecting multiple conductors, which eliminates the need for multiple splices or taps. This simplifies the wiring process and reduces the risk of errors. The power distribution block also helps to reduce space requirements by consolidating multiple connections into a single device. This can be particularly beneficial in applications where space is limited. By providing a central point for connecting multiple conductors, the power distribution block improves safety by reducing the risk of loose connections, accidental contact with live conductors, and other electrical hazards. When selecting a power distribution block, several factors should be considered, including the number of poles, the ampacity, the voltage rating, the short circuit current rating, the conductor size range, and the environmental conditions. The number of poles should be selected based on the number of conductors that need to be connected. The ampacity of the power distribution block should be equal to or greater than the ampacity of the conductors being connected. The voltage rating of the power distribution block should be equal to or greater than the system voltage. The short circuit current rating of the power distribution block should be equal to or greater than the available fault current. The conductor size range of the power distribution block should be compatible with the size of the conductors being connected. The power distribution block should be suitable for the environmental conditions in which it will be installed, such as temperature, humidity, and exposure to corrosive substances. Custom fabricated power distribution blocks can be designed and manufactured to meet specific application requirements. These power distribution blocks can be tailored to accommodate specific conductor sizes, lug types, and mounting configurations. Custom fabricated power distribution blocks can also be designed to meet specific performance requirements, such as high ampacity or high short circuit current rating. When installing a power distribution block, several steps should be followed, including firstly de-energizing the circuit, secondly selecting the appropriate location, thirdly mounting the power distribution block, fourthly connecting the conductors, and fifthly testing the installation. The circuit should be de-energized and locked out before any work is performed. The power distribution block should be located in a clean, dry, and accessible location. The power distribution block should be mounted securely to a suitable surface using appropriate hardware. The conductors should be properly stripped and terminated in the power distribution block using appropriate lugs and connectors. The installation should be tested to verify that all connections are properly made and that the system is functioning correctly. The use of parallel conductors can provide several benefits, including increased ampacity, reduced voltage drop, and improved reliability. By connecting multiple conductors in parallel, the overall ampacity of the circuit can be increased. This allows for the use of smaller conductors, which can be easier to install and manage. Parallel conductors can also help to reduce voltage drop in long circuits. This is because the current is divided among multiple conductors, which reduces the voltage drop in each conductor. By providing multiple paths for current flow, parallel conductors can improve the reliability of the circuit. If one conductor fails, the other conductors can continue to carry the load. When installing parallel conductors, several requirements must be met, including firstly, all parallel conductors must be the same length. Secondly, all parallel conductors must be made of the same material. Thirdly, all parallel conductors must be the same size. Fourthly, all parallel conductors must have the same insulation type. And fifthly, all parallel conductors must be terminated in the same manner. The length of all parallel conductors must be the same to ensure that the current is evenly distributed among the conductors. All parallel conductors must be made of the same material, such as copper or aluminum, to ensure that they have the same resistance. All parallel conductors must be the same size to ensure that they have the same ampacity. All parallel conductors must have the same insulation type to ensure that they have the same voltage rating. All parallel conductors must be terminated in the same manner to ensure that they have the same contact resistance. Conduit size calculations are essential for ensuring that conductors can be installed safely and efficiently in conduits. The National Electrical Code Chapter 9 provides guidelines for conduit fill calculations, including the maximum allowable percentage fill for different types of conduits and conductors. When performing conduit size calculations, several factors should be considered, including firstly the size and number of conductors, secondly the type of conduit, and thirdly the bending radius. The size and number of conductors will determine the minimum conduit size required. The type of conduit will affect the allowable percentage fill. The bending radius will affect the ease of pulling conductors through the conduit. Increasing the conduit size can provide several benefits, including increased capacity, reduced pulling force, and improved heat dissipation. By increasing the conduit size, the number of conductors that can be installed in the conduit can be increased. This can be beneficial in applications where future expansion is anticipated. Increasing the conduit size can also reduce the pulling force required to install conductors. This can make the installation process easier and reduce the risk of damage to the conductors. Increasing the conduit size can also improve heat dissipation by providing more surface area for heat transfer. This can help to prevent overheating of the conductors. In summary, carefully consider the various options and factors discussed to determine the most practical and safe solution for terminating the generator conductors to the manual transfer switches. Consulting with a qualified electrical engineer or contractor is highly recommended to ensure compliance with all applicable codes and standards, and to ensure a safe and reliable installation.